Hello and hi everyone. Today we are going over experiment 5, which is chemical equilibrium. Let's go to the learning outcomes of this experiment. First is to study the effect of concentration and temperature on chemical equilibrium. Second is to determine the equilibrium constant of a reaction. Let's continue with theoretical background. Reversible reaction will reach a dynamic equilibrium when the rate of the forward reaction is equal to the rate of reverse reaction. The factors that affect chemical equilibrium are concentration, temperature, and pressure. For experiment part A, we will identify the effect of concentration toward chemical equilibrium. Le Chatelier's principles state that the change in concentration of any substance in a mixture at equilibrium will cause the equilibrium position to shift in the forward direction or reverse direction to reattain the equilibrium. For part B in this experiment, we will identify the effect of temperature toward chemical equilibrium. Le Chatelier principles state that the effect of temperature on an equilibrium system depends on whether the reaction is exothermic or endothermic. Let's move to the apparatus and chemical reagents needed in this experiment. Now we are ready to run the experiment together.
Let's start with part A. Measure 2 ml of a 0.1 molar iron nitrate solution by using a 5 ml measuring cylinder. Next, measure 3 ml of 0.1 molar potassium thiocyanate solution by using another 5 ml measuring cylinder. Place 2 ml of 0.1 molar iron nitrate solution and 3 ml of 0.1 molar potassium thiocyanate solution in a 100 ml beaker. Add 50 ml of distilled water to reduce the intensity of the blood red solution. Place approximately 5 ml each of this solution into 4 test tubes. Label the 4 test tubes as A, B, C, and D. Test tube D serves as control. Add 1 ml of 0.1 molar iron nitrate solution to test tube A. Compare the color change to that of test tube D, the control. Next, add 1 ml of 0.1 molar potassium thiocyanate solution to test tube B, and then compare the color change to that of test tube D. Add 6 to 8 drops of 2.5 molar NaOH solution to test tube C, and compare the color change to that of test tube D. Now, you can tabulate the observations. Place 2 ml of 0.2 molar cobalt chloride solution into a 100 ml conical flask. Measure 20 ml of 6 molar HCl solution by using a 25 ml measuring cylinder. Add 20 ml of 6 molar HCl solution into the conical flask and swirl. This ensures you have a homogeneous solution. A purple solution should form, indicating a mixture of pink and blue. If the solution appears pink, add more HCl. Divide the purple solution into 3 separate test tubes. Place the second test tube into an ice bath. Leave one test tube at room temperature. Ensure the temperature of the water bath is between 80 to 90 degrees Celsius. Place the third test tube in a water bath within that range of temperature. After some time, remove test tube 2 from the ice bath and leave it at room temperature. Record the color of the solution in test tube 1 and test tube 2. Next, remove test tube 3 from the water bath and leave it at room temperature. Record the color of the solution in test tube 3. Leave the test tubes at room temperature and tabulate the observations. And now part C. Pour the 0.5 molar antimony chloride in 6 molar HCl into a beaker. Pipette 5 ml of the antimony chloride in HCl into a 100 ml conical flask. Set up the apparatus as for titration and record the initial reading of distilled water in the burette. Carefully add distilled water from the burette into the conical flask while swirling until a faint white precipitate is obtained. This is what we want, the faint white precipitate. Record the final reading and the volume of distilled water added to the conical flask. Calculate the value of the equilibrium constant, Kc.
Experiment is done. See you again.